so last time what we did, we jumped into this idea of column space. And the column space of a matrix, this corresponds to all the column vectors within the matrix, and look at the span of those vectors. So you could say it's the span of all column vectors. So if I have a matrix, and if it's a n by m, what that would mean is you're going to have n rows, and you're going to have m columns. So the size of the columns, that's going to be a n by 1. So this right here, the column space would be a subspace, a subset of Rn, not Rm. M talks about the number of vectors you're going to have. And we also talked a little about this thing called row space. The row space talks about the rows within the matrix. You can also define it very similarly. You can say it's going to be the span of all the row vectors. And what's interesting is, what happens when you take the transpose of a matrix? Rows become columns, and columns become rows. So the row space of A transpose really is nothing more than the column space itself. And that's the connection there. We also looked at this idea of a basis. And a basis is a two-part definition. This is something that, yes, you're going to need to know this definition. A basis has to be first a spanning set, and it must be linearly independent. Just because you're a spanning set does not necessitate a basis. A basis is really the minimum set of vectors which will span the space. And as long as you have the right amount of linearly independent vectors, it will span the space. The dimension, again, we talked a little about this term as well. The dimension of a vector space, this is going to correspond to the number of basis vectors. So if I'm in R3, I'm in the third dimension. How many basis vectors do I have? I got 3. And as long as I can find 3 linearly independent vectors within a set, it's going to crank. It will be a basis. It may not be the standard basis, and this is also a definition you need to know. The standard basis in the context of R3, E1 takes on the meaning of 1, 0, 0. E2 takes on the meaning of 0, 1, 0. And E3 takes on the meaning of 0, 0, 1. And if I change the space up to a different vector space, such as 2 by 2 matrices, where I have A, B, C, and D, the standard basis takes on a different role, takes on a different meaning. Here I can look at the matrices, 1, 0, 0, 0, and this would correspond to E1. 0, 1, 0, 0, and this takes on the meaning of E2. And likewise, all the way down. How many basis vectors do I have here? 4. So if I have 4 basis vectors, what does that mean about the space? Which dimension does it reside in? 4th dimension. So 2 by 2 matrices reside in the 4th dimension. What if I had a 2 by 3 matrix? How many entries would I have? I'm going to have 6. What dimension is a 2 by 3 matrix? Where does it reside? In the 6th dimension. And what if I just had a 4 by 4 matrix? Which dimension are you working in? The 16th dimension. This is crazy. We can't go past 3, can we? Or can we? We most certainly can. Okay. In fact, we can go much, much higher if we want to. Make sure you know what it means to talk about the dimension, and make sure you know what it means to talk about finding basis vectors. And again, as long as you find the bare minimum number of linearly independent vectors for that set, for that space, that will constitute a basis for the set. And there's lots and lots of different vector spaces out there. And we've seen a whole bunch of them. The typical ones, R2, R3. If you look at a complex number, how do you write complex numbers? You need a real part, and you need an imaginary part. Typically, you write it in terms of a plus bi. You could take this and you could recalibrate this a little bit differently. And one way of how I can calibrate it is, you could say that I'm looking at complex numbers in which the first entry is the real part, and the second entry, that's the imaginary part. What does that say then about complex numbers? Which dimension do they really reside in? The second dimension. Isn't that pretty cool? All this time you've been working with second dimensional numbers, vectors, you just haven't been realizing it. That's really interesting. Well, if it's second dimension, could you get an idea of what it looks like? Yeah, it's a plane. So how would you graph these numbers? You might look at it in terms of the real axis and the imaginary axis, just like you would for R2. So what does that say about complex numbers in R2 then? They're pretty much the same, or at least isomorphic. That's really, really cool. Well, another vector space which is really, really important is something called the null space. When you hear the word null, what goes through your mind? What do you think about? The void, the abyss, something collapsed down, singularities, black holes, the whole shebang. When you're talking about the null space, you're talking about vectors. It's going to take it and it's going to collapse it down to nothing. It's going to annihilate. So when you have the transformation A, when it operates on the vector x, and it collapses it down to nothing at all, singularity. This is a vector space. That's my claim. How would you prove that claim? What do you need to do? I don't want to show the 10 properties because that's a lot of work for one, but I know that if I have a n by m matrix, n rows in m columns, I know what this says is x resides in this dimension. So I already know that this is going to form some kind of set, and I know it's not the empty set. I know something's in there. What do I know it's in there? The zero vector. Because if you operate on the zero vector, within the space, I'll say OM, I'm saying we're talking about the zero vector from this dimension. This is going to take this, twist it, contort it, bend it, and send it to the zero vector in the nth dimension. Again, if you have a n by n matrix, it is a transformation, it is a mapping, it is this type of multivariable function in which you look at things from the nth dimension, your domain, and your codomain are things in the nth dimension. Well, there's three things again that I want to show. By showing it's a subspace, it inherently shows it's going to be a vector space because this is embedded within that space. You got to show it has a zero vector. Done. I got to show closure. I have two vectors in the null space. I'm not going to pop out and escape the black hole. I'm going to be stuck inside that spot. There's no escaping. And even if I was to elongate, stretch as much as I want to, it's going to suck me right back in to the point of nothing, right there at zero. So by showing all three of those properties, demonstrate it's going to be a subspace, consequently showing that it's going to be a vector space, because all subspaces are vector spaces in their own right. Well, the first property is done, and this is usually the easiest one. It's just showing it has the zero vector. Show that, crank it out fast, and if you don't have that, there's no need looking at anything else. After this, it gets a little more abstract. What you want to do is go ahead and select any vector. So let's we're going to reach inside the bag, close your eyes, fumble around, pick one of these vectors out, and suppose it was something called V. And then once again, I reach inside the bag, close my eyes, pull something out arbitrarily, we'll call it U. So let V and U be something inside the null space. In order to be inside the null space, you got to have a certain characteristic, a certain property. Whenever you operate on the vector, it's going to send it to the zero vector. Okay, now when I'm talking about the zero vector here, I'm talking about the zero vector this from the nth dimension. Because again, if I talk about an n by m matrix, it takes things from the m dimension to the n dimension. That. Now, for the most part, you're not going to really worry about this, but you got to keep this in the back of your mind to try to keep things a little bit more categorized, something that's going to make it so you don't mix things up. Okay, likewise that. And because there is no confusion here between the different zero vectors, I'm just going to not even worry about it. I'm just going to call it 0. I got to show closure. If I operate on the addition of those two vectors, what would I get? Would I get the 0 vector? Or would I get 5 or 6 or something else? What's going to happen? Well, it is a linear operator, that's what matrices are, and since it is a linear operator, I can operate in a linear fashion. I can take it and I can break it apart just like this. But we know that when A operates on B, it's going to get 0. And when A operates on U, 0 as well. We have closure. Once you're inside the black hole, you ain't leaving. You're sticking inside there. Okay, what if you were to try to make a big ladder and try to escape that way? Could it happen? Well, let's find out. You take a scalar, so you let K be any scalar, and we want to maybe designate that. So let's just say K is going to be some scalar. Let's just keep it real, right? True to the game, real to the game. Bad jokes all day long. All right. Scale the vector. It's linear operator again, A. Factor out the K. And what happens when A operates on U? It collapses down to nothing. And when we scale the 0 vector, it stays the 0 vector. So right here, this verifies that this is going to be a subspace. It's going to be a vector space. If it is a subspace, vector space, and we know that every single vector space has some kind of basis to reconstruct all the vectors within the space, how do I find a basis then? But what does a basis mean? Remember the definition? Two-parter. It's a spanning set which is linearly independent. So I got to find linearly independent vectors that span. Okay. Now, just to get us motivated, let's look at this example. Well, what does it mean to be in the null space? So if X resides in the null space, what characteristic must it have? It must be a certain vector so that whenever A operates on it, it takes it, picks it up, bends it, contorts it, compresses it down to nothing. It's got to be 0. Now, guys, pause for a second. We know that if X resides in the null space, it has to satisfy this. How am I going to find this? What is this? It's a homogeneous equation. It equals 0. So what really is this null space? It's a set of all vectors which satisfies the homogeneous equation. Didn't we do this before? Quite a bit. And then everything we talked about in terms of the homogeneous equation, it just starts flooding in as fast as possible. We talked about linearly independent vectors. We talked about free variables. We talked about basic variables. I wonder how all that's going to play out here. Well, let's get cracking. So if I want to solve this, what I could do is I could go ahead and take the matrix A, and I could augment it with a bunch of zeros. I could do that, but I don't really need to go through all this complexity here, putting zeros, because if I do raw operations, I multiply it by 2, what happens to that entry? It stays 0. And if I take 0, add to 0, what happens? It stays 0. So what I could do instead is I just forgo that column, noting that it is there. I just want to interpret it in the very, very end. Take this and solve. How do you solve? Put into RREF. So when you hear the word solve, solve again, synonymous with RREF. Row reduced echelon form. Okay, well, I'm getting pretty excited now. If I take row 1, I add it down to row 3, guess what happens? Bang! 0, 3, 3. And look at this. Those are scalar multiples of one another. Since they're scalar multiples of one another, I know that this is going to zero out. I already know that. And if I didn't know that, I can still say, let's take row 2 and maybe go ahead and reduce it down to 1, and then maybe multiply it by -3, then pivot it down to row 3 to zero out the row. Okay, I have it in echelon form. It's not RREF, but there are some things I can do at this stage right now to talk about this matrix. And one of the things is this: column space. What are the vectors that will comprise, that will span the column space? How would I find those vectors? Take the matrix again, row reduce it down. In any echelon form of work, you don't have to take it all the way down to RREF. This would work just fine because you just want to identify pivot columns. Okay, so if I was looking in terms of the column space, I would say the span is going to correspond to 1, 0, -1, and 3, 2, 0. Pick those two vectors again. Take it, trace it back. And if I want to figure out the row space would be those two vectors. Don't go back to these two because you're not sure if they really are linearly independent or not, but you do know that these two are going to be definitely linearly independent. Okay, there's my row vectors. But again, I'm trying to find a basis set for the null space, so I got to keep pushing on. Put it into RREF and solve it all the way. So if I take row 2, multiply it by -3, and pivot up. Now we're in RREF. Interpret the results. And again, there was that column that was augmented with a bunch of zeros, and if you want to put it there, that's fine. That's perfectly acceptable. So what's the first row right here? What's the first equation it gives you? Interpret what you just did. How many x1s do you need? 1. How many x2s? None. How many x3s? 1. You mix it together, put it in a big pot, stir it around, put it on bake. 40 minutes goes by, and what happens? Bing! 0. We'll do the same thing down here. Take a x2, combine it with an x3, put it in the oven, set it to 400. You get 0 out of it. Now, again, we're trying to find vectors that satisfy this equation. I have the system here, and I can put it in para vector form. And again, what I want to do is take the vector x, just list out its entries, x1, x2, x3. Take what we just found, plug it in. x1 is negative x3. x2 is also negative x3. But what's x3? It's a free variable. It is what it is. And to put it into parametric vector form, one more step. Take the x3 and kick it out. You can kick out the x3, but you can also, if you really wanted to, you can kick out a negative x3 and use that vector. Because again, it's just a parameterization. You can make x3 be positive, you can make it negative. It's whatever you would like to do. If you come back and if you operate, use a vector 1, 1, negative 1, what happens for the first row? Pick up a 1, pick up a 3, that gets you 4. And 4 minus 4 is 0. 0 and 2, add them together, and subtract off 2, you get 0 again. Negative 1, 0, negative 1 times negative 1 gets you positive 1, you get 0 again. So look what we did. We said if you have a vector x, it's in the null space, which equals 0 when you operate on it, it must have this certain structure. It must look like this, otherwise you're not inside the null space. So the null space is nothing more than the span of this vector. And what I want you to do is find a basis for the column space and find a basis for the null space. See what you get. Okay, so if you take the matrix, you row reduce it down into RREF, you should get a form like this. After it's been row reduced down, then you want to do the interpretation. If you want to find column space for the matrix, where you just want to pick up all the basis vectors, all the vectors which can be linearly independent, take it over here, find the pivot columns, column 1, column 2, column 3. They all have a pivot, they have a leading entry. Trace it back to the original. Don't take these again. Trace it back over here and write out those corresponding vectors. First one, because you have one here, you have one here, and you got one here. And if you want to find row space, don't go here, pick the ones over here. And any echelon form would be sufficient, picking the row vectors. You can pick this one, and this one. If I want to find the null space, I'm looking at the span of certain vectors. Again, it's going to be vectors such that whenever I operate, it's going to send me to oblivion. It sends me to 0. Interpret what you have. So take the matrix, put it into RREF, interpret the results, and put it into parametric vector form. And again, the easiest way is to say x1, x2, x3, x4, x5, and then solve for the basic variable. And each equation here, when it's in RREF, will have exactly one basic variable. Solve for it, drop it in. And then with all your might, take it and just rip it apart. Rip it apart in terms of the x4 and the x5. So you need -1, -3, 1, 1, and 0. minus 2, 1, 0, 0, 1. We're going to have minus 1, minus 3, 1, 1, 0. Minus 2, 1, 0, 0, 1. And by construction, as you go about the RREF procedure, the resulting vectors, they're going to be linearly independent. So you just snag and grab them, and you found your independent vectors. Look at this example, and look at the example we did a moment ago. What patterns do you see here? What jumps off the board? Hopefully nothing really jumps off the board. That looks exciting. Free variable present. How many free variables did you have here? 1. How many free variables do you have here? What's the dimension of your null space? What's the dimension of your null space? So what's the connection then about free variables in null space? What conjecture would you make? How about the number of free variables is the dimension of the null space? That's interesting. So the dimension of the null space is the number of free variables. What about basic variables? Because we have those too, right? We have free variables, we have basic variables. Well, how many basic variables do you have here? How many pivot columns do you have? 3. And for each pivot column, it leads you back to a linearly independent vector back here. What's the dimension of the column space? So the dimension of the column space, that's the number of basic variables. In fact, this is of such importance. We don't just say dimension of the column space and dimension of the null space. We give it special names. We call this nullity. The nullity of the matrix A. And we call this the rank of the matrix. What size matrix do I have here? It's a 3 by 5. Which dimension does the column space reside in? What are your vectors? 3 components. This resides in third dimension. Which dimension does the null space reside in? It has 5 entries. So this resides in the 5th dimension. Now, notice this, guys. Over here, I do snag and grab these, and that would correspond to my basis vectors for my column space. Are my basis vectors for my null space, is it what's left over? Are these my null vectors? Is this my basis set for the null space? No. Because what dimension do these vectors reside in? Third dimension. Which space does the null space need to be in? The 5th dimension. So the basis vectors for the null space is not the leftovers. It's not you eat dinner and then what's left over is what it is. That's not it. What you need to do is take this, put it into RREF, and solve the homogeneous equation, parametric vector form. Then you grab those vectors, and those are your null vectors, the vectors that will form the whole entire null space. Okay, now that's a sticking point that a lot of students struggle with. Make sure you remember it. It's not what's left over. It's what sends it to 0. How many different types of variables do we have? You got free variables, you got basic variables. And if you have a 3 by 5 matrix, how many variables are in that system? 5. Some are free, some are basic. What if you were courageous daring enough and looked at the rank of the matrix, which is 3, and the rank or the nullity of the matrix, which is 2, what if you added them up? What would you get? 5. How many columns do you have? So you either have free variables or you have basic variables, and if you add these up, you have the combination of all free variables plus all the basic variables, and what you get is all variables. Kind of a combinatorial reasoning there. So let's really flesh this out. If you have a n by m matrix, how many columns do you have? You have m columns. Variables can be free or they could be basic. So you have basic, you have free, and that constitutes all the variables in the system. But what did the basic variables represent? What would that correspond to? The rank of the matrix. What did the free variables correspond to? Nullity of the matrix. And what you get is an amazing result known as the, not the hippopotamus theorem, it's called the rank nullity, because it talks about rank nullity. Well, let me ask you this follow-up question. Let's say if I have a n by n matrix. So I have a square matrix. Let's say if it has full rank. Let's say it has full rank, that means it equals n. How many free variables would you have? Okay, if you have no free variables, what does it say about the columns in the matrix? If I looked at the homogeneous equation, what will satisfy the homogeneous equation? Only the trivial solution. And if only the trivial solution is going to satisfy the homogeneous equation, what does that say about the columns within the matrix itself? They're linearly independent. So if the columns are linearly independent, could you take the matrix and reduce it down into the identity matrix? And if you take a matrix, reduce it down to the identity matrix, that tells you you're going to have n basic variables. And if you have n basic variables, that means you're going to have rank A has to be n. So if you have no free variables and all the variables are basic, what else does that say about the function, transformation? Every column has a pivot, so it's injective. Every row has a pivot, so it's surjective. So if you have a mapping that's 1-to-1 and on-to, in other words, that's a bi mapping, 1-to-1 correspondence. And if you have a bijective mapping, that means the matrix is invertible. But if the matrix is invertible, what does it say about the determinant of the matrix? It's not 0. So if you have full rank, what it means is that's not 0. Whoa. Interesting how these things just keep coming back around and around again, isn't it? We're looking at the system. What can we say about the system? Well, a lot of things now. If I have full rank, it's going to be invertible. So what if I didn't have full rank? What if I had an n by n matrix and it was a little bit less than it? What's my determinant? Without even looking at the matrix, how would I calculate this? Well, it doesn't have full rank. That means one of the variables must be free. And if I have that free variable, it's game over, guys. This right here does not exist. That means one of the columns is going to be linearly dependent upon the other columns. So it's going to form a linearly dependent set of column vectors. That means you're going to have a free variable. That means the nullity of the matrix is at least 1. That would also mean the determinant, it is 0. Without having to grind through the whole entire calculations, if it's a 10 by 10, 20 by 20, million by million, it doesn't matter. If it doesn't have full rank, determinant's 0. And it's not invertible. Now, these things right here, yeah, you're going to need to know how to maneuver and navigate through those different types of things we just talked about. Make sure you do know the rank nullity theorem right here is really, really important. One way of how I can state this is I can say, suppose you have a by 7 matrix. And let's say it has rank 2. What's the nullity? 7 minus 2. 5. Okay, not too bad. And what if the nullity actually is 0? Describe the null space. What is a null space? It's all the vectors that when you operate on it, it collapses down to nothing. The singularity. It terminates, goes to 0. Okay, well, this talks about the number of linearly independent vectors. How many linearly independent vectors am I going to have? Nothing. There's no linearly independent vectors. So what would this be? Again, you're solving the homogeneous equation. This always has a solution, namely the trivial solution. So what is the space then? It's the span of 0. That's all there is. It's just that 0 vector in that space you're working with. Whether it's going to be, if we say m by m, it's going to be the 0 vector in the mth dimension. If it had something else, like 1, 2, 3 for a vector, well, that's going to be linearly independent by its own right, by itself, and that would be not 0, but at least 1. Okay, that's really cool. Wow. I wonder what's going to happen next. I'm sad to say you have to wait to find out. You guys have a great day.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.